So and finally, in our final example 5, we're going to do something called a logistic growth model. So in the real world, populations don't grow uninhibited. So in other words, the population doesn't do this forever. Stop and think what would happen to our planet if that were true. So in the real world, there are things that limit how large a population can get. And for animals, the things that limit them would be the amount of oxygen, right? The amount of water, the amount of food, the amount of nesting or places to have your babies, those kinds of things. So what that does is that takes this population growth that looks like this and it levels it off to a specific point in terms of population. So this point up here, this Y value would be the carrying capacity. That's how many animals that environment can support. So there's a carrying capacity for humans on our planet, and we are fast approaching it because we're running out of things, resources. So there's a carrying capacity for pretty much everything. If you put a bunch of, bacteria into an enclosed dish, you can only grow so much because at some point they're going to run out of food and possibly oxygen, and they'll die off. So you can see it. So for this particular one, we're talking about bald eagles. We've got 6 of them. We've captured them and set them, transported to Montana and set them free. Based on experience, the environmentalists expect the population to grow according to the model. P of T is equal to 500 all over 1 plus 83.33 e to the negative 0.162 t. And there's our logistic growth model. Now you're going to look at this and say, well, wait a minute. You told me that if I had a negative exponent on my e, that it would be decaying, it would be getting smaller. Yeah, but this is in the denominator. So if you take something that's getting smaller in the denominator, think about fractions and the fraction itself, what happens to 1/3, 1/4, 1/2, those kinds of things. So as that denominator gets smaller, the overall fraction is going to get bigger itself. So that should make some sense, especially because we don't have a 1 sitting up here, we have 500 sitting up here. So we're going to divide that 500 by smaller and smaller numbers. The overall population is going to get larger and larger. Maybe that's a better way to say it. Okay, so the very first question is asked us to determine the carrying capacity. So the carrying capacity is what happens as t approaches infinity. So again, as we get bigger and bigger in terms of time, what happens to our population? Well, we can do this verbally. We don't need to work this out in terms of mathematics. So what they're saying is t is going to get huge. Well, that's going to make this negative number get huge. And e raised to a negative number getting bigger is going to get tinier. And hopefully that makes sense. Because remember when we took and did negative exponents, the output on those exponential functions were fractions. So again, this is going to go to 0. Okay, well, that means the 83.33 times 0 would be 0. So we're going to end up with the population being the 500 all over the 1 plus the 0. So that's going to be 500. So in other words, the number in this problem, the numerator, is our carrying capacity. So at most, this territory or area can support 500 bald eagles, and that's what that's saying. Part B is asking what's the growth rate. So part B is asking for the growth rate. So even if it's down there sitting as a negative exponent, you're still going to pick up the 0.162. So 0.162, which is 16.2% growth rate, which is pretty big if you think about it. 16%, that's huge. Part C is asking what's the population after 3 years. So part C, we're going to find P of 3. So we're just going to plug in 3 for T. That's 500 over 1 plus 83.33 e to the negative 0.162 times 3. Now, when you do this on the calculator, make sure you get the entire denominator in a set of parentheses. So 500 and then divided by parentheses 1 plus 83.33 e. Then up there in the exponent, you've got negative 0.162 times 3. And if you do that, you end up with 9.5. So we're going to round that up to 10 eagles, which isn't too bad. In 3 years, our 6 eagles are now 10 eagles. So we've gained 4 of them, right, to maturity. Okay, part D, we want to know when the population is going to reach 300 eagles. This I need a little bit more room for. So we want to know when this function is equal to 300. Okay, so they're asking me to solve for time. So we're going to set 300 equal to 500 all over 1 plus 83.33 e to the negative 0.162t. Okay, got to solve it for time. So the very first thing you would do is clear the fraction. So we're going to multiply both sides by this denominator. So that would give me 300 times 1 plus 83.33 e to the negative 0.162t is equal to 500. Okay, so again, solving for t is now inside parentheses. We're going to divide out this 300. So we'll have 1 plus 83.33 e to the negative 162t is equal to 500 divided by 300. That would be 5/3. I'm just going to cancel out the zeros. I'm not going to take that to a decimal because it's a repeating decimal and I don't want rounding error. So I'm going to leave it as 5/3 until we're done with the calculation. Okay, then you're going to subtract the 1. So minus 1, minus 1. We'll get 83.33 e to the negative 0.162t is equal to 5/3 minus 3/3 is 2/3. Then we're going to divide out. So we now have e to the negative 0.162t is equal to 2/3 over the 83.33. And I know that that is ugly, but we're going to work with that. Then we're going to come in and take the log of both sides. So on the left side, once we've taken the log, we'll get a negative 0.162t. I should write that bigger, sorry. So negative 0.162t is equal to the natural log of, that's 2/3 being divided by 83.33. Now, if I didn't have a calculator, I would worry about cleaning that up. But because I'm just going to go to the calculator, I'm not going to bother to clean that up. And we're going to divide that out. So t, when it's all said and done, is going to be the natural log of the quantity, 2/3 divided by 83.33, all over negative 0.162. So now you're going to head to the calculator. And again, you should be able to put this in just like it says. So take the natural log, start the parenthesis, so the 2 divided by 3 divided by 83.33, and then close the parenthesis, and then divide by the negative 0.162. And what you will end up with is approximately 29 years. So in 29 years, our population started with 6 is going to be at 300 eagles. So quite a bit in just 29 years. Okay, we're going to do this one more time on part E. It says, how long will it take for the population to reach 1/2 of its carrying capacity? Well, if the carrying capacity is 500, half of that would be 250. So we just did 300. Now we're going to go do 250. Same exact process. So it just gives you another chance to solve this equation for time. Okay, well, we saw last time that what we did first was clear the fraction, and then we ended up dividing this out. So I'm immediately just going to flip these two. So it's something to start looking at in terms of trends and what's happening. So I get 1 plus 83.33 e to the negative 0.162t is equal to 5 divided by 250, which is 2. That's, believe it or not, half the capacity. Okay, now we're going to subtract the 1. That's going to give you 1. So 83.33 e to the negative 0.162t is equal to 1, dividing. So we now have 1 divided by 83.33. And then we come and take the natural log. So again, it's the same process over and over and over. It's going to be the natural log of 1 divided by 83.33. Then we'll divide out the decimal. So t is going to be equal to the natural log of 1 divided by 83.33 all over a negative 0.162. You'll notice your signs are working out because you're taking the log of something that's much less than 0. That would be a negative quantity divided by a negative quantity is going to give us a positive. And I got 27 years, which makes sense because we know that it took 29 years to get 300. This is 250 of them, so it should be a little bit less than that. And that's a logistic growth model, another way of looking at an exponential function. And that wraps up chapter 6. Thank you.